Alright, so this video lesson is going to be expanding upon the Bohr model and what Niels Bohr discovered with electrons within the atom. But before we get started, y'all have to see this. Oh my goodness, I'm so cute. Look at the little Frenchy puppy. Yay! I have 9 of these right now. Aren't I precious? Look at my little paws. Oh my goodness, so cute. Say bye-bye. Okay, so here we are. We are ready to go now. Had some technical difficulties with my recordings, and anyway, long story short, here we are. So we are about to go over a couple of chapters where we discuss electron arrangement and electron cloud. The arrangement of the electrons is really important because it has everything to do with the behaviors of an atom, all right? So before we get into Bohr and how he developed his model, it's important that you get some background information, stuff that you may or may not have been taught. Most of the times it's been my encounter that students have not been taught this before, okay? So what you see right here, what you see is a rainbow, all right, a rainbow of colors. But what a lot of students might not know is that when we perceive white light, so the light in this room, the light from the sun, the light outside, our brains perceive white light. However, that's what our lenses interpret, and that's what our brain perceives. However, white light, visible white light, actually contains all the colors of the rainbow. That is red, orange, yellow, green, blue, indigo, and violet. All right, so in order to see all the colors in the white light, we actually have to hold a prism up to our eyes or use diffraction lenses to actually see all those colors, all right? So visible light is just one form of wave energy. So this right here is what is known as the electromagnetic spectrum, okay? So this is energy that comes in the form of waves, all right? And this one little section right here, this little section right here is the energy that gets released as visible light. Everything else we cannot see, all right? So a couple takeaways from this image that we want to see is that there are other forms of energy that we should be familiar with that are also wave energy. So it's energy that's in the form of a wave, all right, and that is gamma rays. So this is we've talked about gamma rays because they get released in radioactive decay, but gamma rays can be harmful. They're very strong, and it's used in treatment of radiation during chemotherapy and that sort of thing, all right. X-rays, also stronger on the visible spectrum. Ultraviolet light, we cannot see UV light, but it is very close to the visible light spectrum. All right, that is what we can see. Now, on the other side, that is less energy than visible light would be infrared light. And then radio waves, radar, TV waves, microwaves, that's all going to be over here on this end of the spectrum. So basically, what's of great importance is this wavelength, okay? So notice how down here on this end with gamma rays that the waves are very tight and very close to one another, and that's because they are associated with high energy, okay? So this is a huge concept that you need to know. So high energy or big energy is associated with small waves, releases small waves, okay? Low energy, okay, releases big waves, all right? So this is an inverse relationship because usually we would think, oh, high energy, that's going to be a big wavelength. No, that's not the case. High amounts of energy are associated with small, tight waves, okay? And then lower amounts of energy. So if you've got, like radio waves are big waves, all right, with not a whole lot of energy, okay? Gamma rays, however, though, are tight, small waves with high volatile amounts of energy, okay? So just know that inverse relationship. You can see that as one is increasing, the other one is decreasing, okay? So energy's low, the wavelengths are large and big. Over here, so the wavelength is the distance from one end of the wave to the other. So you can see these smaller waves are associated with high energy, okay? So this is all important because this is going to directly link up to our discussion with Bohr and the emission spectra and how he discovered energy levels, those rings around the nucleus, all right? So let's get back to the visible light for just a second. So you can see that violet, this is, NM is nanometer, all right? So nano is a really small measurement for length, all right? So, but we are talking about energy waves, so these are really small, all right? So violet light is going to be the smallest wavelength of color on our visible spectrum. But remember, small waves mean big energy. So of the colors on our visible light spectrum, purple or violet is the strongest, okay? So it has the highest amount of energy associated, but it's the smallest wave. Now we go to the opposite end of our visible spectrum, and you can see that red light, okay, is going to have larger waves. So we've got 700 and then about 720, 740 nanometers. So between about 380 and 740 nanometers, we can actually see, all right? Everything else, all this other energy outside of this little sliver, all right, we cannot see, all right? It can be detected with equipment, but we cannot visibly see it. So red light is going to be associated with the lowest amount of energies, but the biggest waves, okay? So wavelength, so you've got small, tight waves, and then they start to get bigger and bigger and bigger, okay? So high energy, low energy, big wave, length, I'm just going to put wave, small wave, all right? So this is important because we're going to come back to this concept and how it connects to the Bohr model and the emission spectra that Bohr discovered. Okay, so what you see pictured here are two separate Bohr models. One is of the element hydrogen and one is of the element magnesium. Now, yesterday we reviewed this, and prior to the break we talked about how the number of energy shells that an element has depends on the period that it's in on the periodic table. So for instance, hydrogen is in row 1 or period 1, so it has only one energy shell. Magnesium is in period 3 or row 3, so it has 3 energy shells. Okay, so we can see it's got 1, 2, 3. Now, I'm going to throw out some terms here that you're going to need to be familiar with and know about. All right, so first of all, if you see E1, E2, E3, all right, and right here, E1. So if you see just an E, that is just an abbreviation for energy level, all right? So just be prepared. If you see this, be familiar with it. E1 just means energy level 1. E3, energy level 3, okay? Now, what we call both of these atoms and their electrons right now, they are in what we call a ground state. So you're going to hear that term, that phrase a lot, all right? So these are both in their ground state. This is ground state hydrogen. This is ground state magnesium. So what it means to be in the ground state, that is the typical everyday state. So this is what a magnesium's electron cloud looks like when it is in just a neutral everyday state. No energy has been added or absorbed. It's just in its ground state, right? So this is the typical placement of its electrons. So this is what it should look like. Same thing for hydrogen, all right? Now, so I wanted to throw that out there. The other thing that I'm going to throw out, which is a huge concept right now, in both of these images, and this is something that Bohr was able to determine with his study with the emission line spectra, which we're about to go over, is that energy, so y'all know the difference between kinetic and potential energy. Kinetic energy is the energy of movement. Potential energy is like stored energy. So these electrons, okay, so for instance, this electron right here in hydrogen has a certain amount of stored potential energy. All right, same thing here. These two electrons have a certain amount of stored energy. These 8 right here have a different amount of energy. So that's why they call these energy levels or energy shells. The energy is different at each level, and it increases the further you get away from the nucleus. So really important here, energy increases as we get further from the nucleus. Okay, so the energy state of the electrons is lowest here, and it's highest in the valence shell. So big surprise, all right? So, but the electrons, these two valence electrons, have the highest energy of any of the electrons, okay? Because they are in the furthest out energy shell, all right? So that's another fundamental concept. All right, so before we move forward, I want to ask you a question, all right? I'm obviously not going to get an answer back, but just something to think about when I ask this. So Niels Bohr, when he was studying electron arrangement in the atom, he was building upon other models, okay? So J.J. Thomson, John Dalton, Ernest Rutherford had, particularly Ernest Rutherford, had a model where he determined that the electrons are actually orbiting the nucleus. But Niels Bohr went a little further and wanted to say, okay, well, are these electrons orbiting in specific positions outside the nucleus, all right? When he did this, which element do you think he chose? If you want to study electrons and how they're arranged, okay, what's going to be the best element to study? Well, the best element for him to study was hydrogen, okay? The reason why is because hydrogen only has 1 electron. So he was able to isolate and actually study it a little bit better than he would say magnesium. Magnesium has like 12, okay? So he used hydrogen gas. That is the element he started with. And beyond his discoveries with hydrogen, other scientists were able to put together the energy shells and energy levels of all the other elements, okay? So let's dive into that. Okay, so I don't want anyone to get overwhelmed with these images. We're going to get to this right here, what's going on in this image in just a second, but let me give kind of the background of what Niels Bohr did. So this is an actual more sophisticated machine that we actually use today when we do this lab. But essentially what's inside this is called a spectral tube, and what's inside of it is hydrogen gas. And so Niels Bohr, with the technology he had at the time, did something similar with hydrogen gas. So he used an electric current, so he used electricity to actually add energy and run electrical current through the hydrogen gas. So here's what happened, okay? So that 1 electron that's in all of these millions, billions, trillions moles of hydrogen atoms is it started absorbing that energy, okay? So what's important to realize is that the electron had to absorb a certain, what we call quanta of energy. So that's an important word. So a quanta of energy is a distinct, specific amount of energy, bundle of energy, okay? So for the electron that in hydrogen, it has a certain amount of potential energy in its ground state. So absorbed energy, that is energy coming in from this, it's actually electrical energy, okay, from the electrical current, that 1 electron was absorbing energy, and once it got a certain quanta, what we call a certain quanta of energy, it would jump in between energy shells, okay? So let me, okay, so I wanted to get rid of that image because I felt like it was a little too busy. We weren't ready for that yet. So, so again, electricity is an electrical current, which is a form of energy. Electrical energy is being added, okay? So keep that in mind, all right? So this electron, let's say that to be in this energy shell, so this is energy level 1, okay, that it requires, and again, I'm just making up these numbers for explanation purposes. Let's say that it has 100 kilojoules of potential stored energy in that shell, okay? Now, I'm going to draw some additional shells out here, okay? So this is going to be E2, this is going to be E3. Now, Hydrogen doesn't typically have these shells in its ground state, but now we're talking about actually adding energy, so we're going to introduce something known as the excited state, okay? So if it's 100 kilojoules of energy that electron has here in energy level 1, let's say in order to be in energy level 2, you need 250 kilojoules of energy, okay? Not 251, not 249, but exactly 250 kilojoules of energy, okay, in order to be in that energy shell, energy level 2. So, again, just making up these numbers to make this explanation. So, let's say this electron absorbs exactly 150 kilojoules of energy, because that's what's going to allow it to go up to energy level 2. So once it absorbs that quanta, remember it's called a quanta of energy, that specific amount of energy, it will go from energy level 1 up to energy level 2. Now once this electron goes up to energy level 2, this is what is known as the excited state. Okay, that higher energy level is known as the excited state. Well, here's the thing about the excited state. Electrons don't stay there, okay? They do not stay in the excited state because they're not stable there. They will immediately fall back down, okay? So this electron will then go back to its ground state, okay? Just instantaneously. I'm showing you guys this slowly, but this happens very, very quickly in a matter of like nanoseconds, okay? So that electron goes back to its ground state. So here's what happened. Remember, it had to absorb a certain quanta of energy, and in this case, it's in the form of electricity. So it absorbs that quanta of energy to jump up. In order to fall back down, that is to go to that original ground state, back down to energy level 1, it has to release that exact same quanta of energy. So if it was 150 kilojoules of electrical energy that it absorbed to go to that higher energy state, it's going to release 150 kilojoules of energy, okay? However, here's what Niels Bohr noticed. He noticed that whenever the electrons fell back, that they were releasing specific colors, okay? Specific colors of light. Now, I'm going to go back to that other image, because I feel like we're ready for it now, okay? So what he was noticing is that when they fell back from their excited state back to the ground state, they were emitting that electrical energy is now being transformed into light energy that they're releasing out. All right, so here we go. Notice in this image that it's showing, let's say that this electron goes from energy level 2 to energy level 3. When it falls back, it releases red light. When it goes from energy level 2 to energy level 4 and falls back down, it releases a bluish green, like teal colored light. When it goes from energy level 2 to energy level 5, it falls back and releases violet light. All right, and then again, this is another form of violet color right here as well. It goes energy level 2, past, beyond energy level 5, and then comes back, okay? So this right here is what Niels Bohr saw, okay? When he turned the lights out, he was viewing that spectral tube through a prism, through a diffraction lens, he saw these 3 pencil beams of color, all right? So going back to what I introed this video with, we talked about how energy and wavelengths of color vary, right? So notice how the biggest jump from closest to the nucleus where energy is low, further out, which is higher energy. Notice how when this electron came up here and fell back, that it released violet light. And remember how we said violet light, how I was telling you that violet light is a smaller wave, tighter wave, but it's big energy, okay? So energy is higher the smaller the wave is. That's an inverse relationship, okay? Notice that the smallest jump produced red, which makes sense because that's a bigger wave, and big waves, okay, are associated with lower amounts of energy, all right? So how does this support the idea of energy levels? Well, this is how it supports the idea of energy shells or energy levels. These electrons had to absorb a certain quanta or amount of energy in order to make that jump. And that exact amount of energy is associated with a certain color on our visible spectrum. Now, what's crazy and what's interesting is that it's not the same for all elements. So for instance, let's say going from energy level 2 to energy level 4 in a hydrogen atom releases, when you fall back, when the electron goes back to its ground state, it releases this blue-green color. But let's say in a nitrogen atom, when an element goes from, say, energy level 2 to energy level 4, and it falls back down, that it releases blue or yellow or orange, okay? So what's important to realize is not every element's electrons absorb and release the same quantities of energy. So to be an energy level 1 of a hydrogen atom, it might require 100 kilojoules of energy. But to be in the energy level 1 of, say, a nitrogen atom, it might be 725 kilojoules of energy. So the energies that are required to be in the energy levels for each element is different, okay? So, and I'll show you what that looks like. Okay, so I love this image. This image is showing you if we took every single element from the periodic table and we added energy, excited those electrons, and they start jumping up to an excited state and falling back down, these are the lines of colors that they would produce, okay? So you can see that some of the transition metals produce some very vibrant colors, okay? So it's different. The quantized amounts are specific to each element. Now, however, do understand that, so for right now here, this is scandium, all right? Every atom of scandium will produce these same pencil beams of color. But those pencil beams of color are different than the ones that titanium produces, which is next to scandium, okay? So Niels Bohr was able to determine that electrons are in specific quantized shells of energy because they produce lines of color specific to those energies, all right? So let's review real quick, because these are the top things that you need to know for your mini quiz and from this very, I want to say complicated, but it's kind of some new stuff from this video lesson. Okay, so take-homes are this, all right? The further out that you get away from the nucleus, the higher the energy is, okay? Energy shells can be listed like this, E1, E2. You can see in this image that they're listed as like N1, N2, N, okay? Those are just energy shells, okay? Now, atoms will absorb energy and go from a ground state to the excited state. All right, so they absorb energy, whether we're heating it or adding electricity like Bohr did. It's going to absorb energy, all right? It's going to go to an excited state. It's going to immediately fall back, okay, to its ground state. And when it falls back to its ground state, that is when the atom emits energy in the form of a wave. Now, some waves are not visible, but these waves are, okay? So the waves get emitted, and if it falls on our visible spectrum, then we see spectral lines of color, okay? Red is our largest wave on the visible spectrum, okay? So larger wavelengths mean low energy, okay, which are shorter jumps. So for instance, if an electron goes from, say, energy level 1 to energy level 2, it's going to produce a lower energy wave, like red, okay, when it falls back down. But if it says, let's say that it goes from energy level 1 up to energy level 5, okay, so it goes from here to here, when it releases light back out, it's going to release a stronger wave of color, like blue or violet, for example, okay? So big jumps are going to require lots of energy, but be smaller waves. Okay, so small waves, big, long jump, high amounts of energy. Okay, so those are the take-homes. That's pretty much it. There will be a mini quiz to follow, and then we will practice some more tomorrow in the Zoom call.